there is another concept which is called the prediction interval, and you can take a look at this and let me know if you have questions. I might ask the TA to go over it in the discussion. So the difference between this concept and the confidence interval for the mean function is that here we are trying to build a confidence interval for the observed value of y for a new data or a new data point. And the new data point has a piece of noise here. So there's this regression function evaluated at the new point. So you can compute this and you can build a confidence interval for this. Sorry, you can't compute it, but you can build a confidence interval for this centered at mu hat x nu. But the y mu has an extra piece of noise here. And so if you want to build a confidence interval for that, for this guy instead of this guy, then your confidence interval would have the same center if you go through the calculation, but the length would be bigger. So you'd have to account for this extra variability caused by this. And so the effect, once the dust settles, is that you just have this extra one added to the this term in the standard error. So if you compare with the previous, so if you do it for the regression function, there is no +1 here. If you do it with for the observed value of y, you get an extra +1 because you would have this extra piece of noise that you have to account for. So I'll let you look at this. There is a discussion of this in the lecture videos. And if you have questions, you can ask either in the next lecture or in the office hours. Sounds good? So last chance to ask any question about any of these ideas. Otherwise, we're going to move on to the next topic or the next chapter. Which is going to be testing a general linear hypothesis. So no questions, comments? Okay, so what I'm now going to do is discuss this idea of testing a general linear hypothesis. And this is, I would say, a very general, very useful concept. So the idea was that for the, like in the previous discussion, we developed tools to do hypothesis testing of this form. So let me open something here. So did any of you guys get a chance to actually look at these before we start? So I asked you to take a look at lecture 14. So did you get a chance? Anyone? Okay, Anna Avery. So one of you wants to maybe tell us what was it about? I just want to hear you guys. What are your thoughts? So what did you get out of that lecture? Can you maybe just, yeah, go ahead.
Yeah, so I think like the main point of the lecture was about testing general linear hypotheses, which like basically have to do with when you maybe have multiple constraints. So your null hypothesis might be like a system of linear equations. And so that lets you write your null hypothesis as like potentially the matrix A times your vector of betas equals 0. testing that against like the alternative of A beta is not 0. Yeah.
So before we start, can you give an example? For example, what would something like this look like? Anna?
Do you mean like what the matrix A would be, or like what the constraints are?
Yeah, what are the constraints, let's say?
I think an example could be like beta 1 equals negative beta 3, and then like, or negative beta 2, and then beta naught equals 0, something like that.
Okay, great. So, so how many constraints does this have? Or
I think 2, right? 2 constraints.
yes, so we have 2 constraints, 2 linear constraints. Okay, that's great. So what else do you want to tell us? You're saying something? I interrupted.
That's basically where the lecture video started. I guess, so the matrix A would be like, in this case, so if you have a linear model that just has beta naught, beta 1, beta 2, your matrix A would be like a 2 by 3 matrix.
Great. Okay, so beta is, yeah, beta naught, beta 1, beta 2. So what would that matrix be?
I think 0, 1, negative 1 on the first row, and then wait, hold on. Would it be 1, 0, 0 on the second row? Or yeah, 1, 0, 0.
Yeah, it's almost correct. I think this has to be 1, because once you multiply it, so you want to say A beta is equal to 0, that would be equivalent to beta 1 plus beta 2 equal to 0. And then beta 0 equal to 0, which would be equivalent. If I haven't made a mistake. Okay, great. So what else? So let me ask everyone, so far so good. So that's exactly what we're talking about. So we're trying to do a hypothesis, something like this. So our null is something like that. So what is the difference between this and what we were doing before? So why do we need something new here? Anyone? Why can't I use what we developed so far to deal with this problem? Any thoughts?
Because if you separated it into like the 2 constraints into 2 different problems, and you just did 2 t-tests, it will affect your type 1 error. And so by doing it this way, I think it doesn't.
It would do what?
Well, if you do 2 t-tests, both at alpha like 0.05, like your probability of like it kind of changes. And so this kind of solves that, I think, or it's just more convenient.
That's actually a great point. So let me. So there are a couple of interesting points in Avery's response. So why do we need more tools? Why not do 2 separate? I have to Google what it is, sorry. Okay. T-tests, okay. So first, we can do these using t-tests. so this should be obvious that this hypothesis we can do using t-test. How can we do a t-test for this? Maybe Avery, you want to comment? Why can, yeah.
Can't you just, make a vector that will multiply by the beta vector to kind of represent that, and then figure out the distribution from there?
Yeah, great. Okay, so I can do something like this. Basically, in fact, the first row of this here times beta. This would be 0, 0. So actually it is. Yeah, and this is something like A transpose beta equals 0. And we discussed that you could do t-tests for these. Basically, you can do a plug and estimate for this and then obtain the distribution of a studentized version, which would be a t-distribution. You can just do either develop hypothesis test or a confidence interval or something like that. So that was a great point. So we could do t-tests, separate t-tests for these two. Now, can you say that again, why this might not be ideal?
Because if you're doing two t-tests, both at alpha level of 0.05, it's like a 95%, or your type 1 error is 5%. But if you're doing it twice, it doesn't stay 5%.
Great. Okay. So is there a way to fix that?
I think you can like adjust it, but I'm not exactly sure what that adjustment is.
Okay, great. Yeah, so that's one of the issues. So if I, so what we're trying to test here is, you can think of it as the intersection of two events. So that holds and this holds. And here you're testing them separately. So this event and this event. So if you test both at level alpha, there is no guarantee that your level for this would be alpha. So can anyone argue that? Can we somehow formalize it and see how we can deal with it? This was actually not part of lecture 14, but it's something good that came up. And I usually don't discuss it. But there is a way of fixing this. Anyone can enlighten us? I'll let you think a little bit about it. No one? Let's see. there is anyone in the chat. Anyone can enlighten us a little bit about what is going on? And
well, I kind of remember something in like my 102, no, yeah, 101B class where I think my professor derived doing like multiple t-tests like 20 times with a type 1 error of 5% ends up giving you like a type 1 error of 49%. He did that. I think he used the binomial theorem to show that, but I don't remember the exact steps he did. And then he introduced the f-tests afterwards, which ends up fixing the problem in a simpler way than just fixing the alpha for multiple t-tests.
okay. Using the binomial distribution. So I'm gonna say this was in 101B.
Yeah, it was in 101B, I believe.
Okay. So one way to deal with this is to just think of. So you have a the simple way of doing it is like I have a test. So delta 1. Let's say this is takes the data. I'm not going to show it, but takes the data, and you have a statistic that sort of say T1 is bigger than tau 1. So you'd output 1 if this holds, otherwise it's the indicator, otherwise 0, and then you'd have a delta 2 that says I'm going to output. This is a different T statistic. I compare it with the threshold, and you output 1 if you reject 0 otherwise. And let's say these are designed for, I'm going to write it like this. Sorry, H1, H02. So this is H01, this is H02. There are two hypotheses and two null distributions. So the second index is the indices of hypothesis. So what I design is I have a test that says delta 1 is 1, under null would be alpha. The way I set the threshold guarantees that my first test, the chance that it's equal to 1, under null is alpha, and then I'd have another test, the second test, under the second null. This is going to have a type 1 error of alpha. The way I set these thresholds, I can guarantee this. So now what I want is, so what I would, so this is the test. So like a delta, the test for so based on these two tests, how would you construct the test for, so how do we construct the test for delta, sorry, for what I want is for H null intersect with H2. So under both of these. So what is a reasonable test? If I have these two tests, this tells me whether the first null occurred. This one tells me whether the second null occurred. So what is a reasonable test? Okay, so now I see something in the chat. Multiple t-tests increases chance of like, yeah, so that's what we are trying to deal with. So we're trying to see if we can build it. So what is first the best, what is a good test based on, if I give you these two individual tests, how do you devise a test that tells me what I mean that test this hypothesis? Anyone? Based on the output of delta 1 and delta 2. Anyone okay with this notation? This is the indicator notation. This is saying that delta 1 is 1 if this holds and 0 otherwise. This is saying delta 2 holds is equal to 1 if this holds and 0 otherwise. So this is how you can write compactly the test. This is like a t-test or whatever that compares some statistic with the threshold. So how do you do these two tests? How can I build a test for this hypothesis? This should be simple, right? How do you combine these two? So you can perform these two tests and you get either 0 or 1. So there are 4 cases, right? So delta 1, delta 2. It can be both 0, 0, 1, 1, 0, 1, 1. So how do you decide? They're not independent, no, they're based on the same data. They're going to be based on the same observations. But let's say if both of them are 0, should we say the null is probably okay or the alternative? Okay, we run both t-tests and reject only if 1-1 situation happens. So that's, yeah, there are different ways that you can approach. So you can say, we reject if both of them happen. But why not these? Why not consider these cases? So when one of them is 1, it's saying that one of these is violated, and we want both of them violated. So you could reject based on only this guy, but you would lose information. This is saying only when both are violated, when both of these conditions are violated, then we should reject for the null. But reject for that, sorry, reject the null for the alternative. But you're testing whether both hold. And so if either one of them fails, then we can reject. So it's better, that would be a test, valid test, but it's better to reject when these 3 cases happen. Okay, so I would devise a test that tells me delta is going to be 1 if delta 1 is 1 or delta 2 is 1. Okay, something like that. Does that make sense? Okay, makes sense to reject that in that case. So when one of them is 1, it means that the corresponding null hypothesis is violated. So both are not the case. So if that's the case, then the probability, like the type 1 error of this, would be this, which is the probability that delta 1 is 1 or delta 2 is 1. Okay. So this is, you can think of this as the union. Union of these 2 events, right? So how do we break this probability into, how to break it into these 2 pieces? Can I do this? The probability that delta 1 is 1. The edge intersect the edge 2. And then the probability under H1 intersect H2 that delta 2 is 1. How do I break it into these two pieces? Would it be equal? Something like this is correct. Anyone? Hello? Who remembers the basic probability? Can I say probability of A union B is equal to probability of A plus probability of B? Is this so? Minus, okay, minus the probability of A intersect B. Is that okay? Max, do you want to comment? Yes, okay. So I need to subtract something, but I don't know this probability. I don't know. So this goes back to Avery's question. So in order to figure this out, I need to know the joint distribution of these two. Or let's say one way of knowing that is if they're independent. They're not independent in this case, but I don't want to figure out the joint distribution. So is there a way that we can find an upper bound to get rid of this? I'm okay, because we're controlling the error, I'm okay if I have an upper bound. Can we find an upper bound? Do people know what an upper bound is? Anyone? Max, Anna, Avery, the active people in class? Or others? Jonathan, Matt? Matt was active too, okay. So how do we get an upper bound? I want something which is bigger. Lower bound 0. Okay, so one lower bound is 0, another upper bound is 1. That's perfect, but it's kind of useless in this case because I don't want to upper bound the error by 1. I know it's going to be bounded by 1. I want to make sure the error is small. Anyone remembers union bound? Have you heard about union bound? I guess not. Okay, so this is less than or equal to PA plus PB. Anyone can justify that? Oh wait, there is an upper bound. Minimum. A minimum is not an upper bound. It's a lower. It's not even lower bound. So it's close, but the sum of the two would be an upper bound. Why would that be correct? So this is called the union bound. It's a very useful concept in probability. Why this is valid? Okay, math, great. So this can't be negative. So this is non-negative. So you're subtracting something which is in general positive. Okay, Sophia says the same thing. Good. So it's just gonna just make it smaller. So this, if I drop this term, it gets bigger. So this is a very useful bound. It's just I can't emphasize how useful this is. This allows you to deal with the union of two events, the probability, without knowing something about their joint behavior, or at least just ignoring that. So if I ignore that, I can just do this, and this is union bound. So what do we know about these individual ones? So let's say I guarantee that these are less than, not necessarily equal, but I'm going to guarantee that these are less than or equal to alpha. what can I say about this there? Yeah, so this is going to be upper bounded by alpha because this is saying under the joint, assuming that both H0 1 and H0 2 are okay or correct, then what is this probability? I know that whenever H0 1 is correct, this is bounded by alpha. So this is even better. So I have more information, which I don't need. So this is going to be upper bounded by alpha, the way we designed it. And so if I do this here, this is going to be also bounded by alpha. So this is going to be at most bounded by 2 alpha. So that's the guarantee that I would have. Yeah, so now let's say if I want to make sure that this type 1 error probability is bounded by alpha, what should I do? This turns out to be 2 alpha. What can I do here? Any idea how can we modify the original tests so that this becomes alpha?
You can just use alpha, well, change the original alpha to be alpha over 2, so then it's bounded by alpha.
Great. So I'm going to, instead of testing the original ones at level alpha, I'm going to test them at level alpha over 2. So this would be alpha over 2. This would be alpha over 2, and this would be alpha. Okay. So I have to test the original hypothesis at a stringent level, more stringent level. And so you have to set the threshold such that this is alpha over 2. And then you have a guarantee. This could be in general smaller, but at least this way you're guaranteed that your type 1 error for this joint test, which rejects if either of them. So this, you reject when either of them reject, this would have level alpha. So this operation has a name. So does anyone know what that is? What is the name of this thing that we did here? This is someone's correction. Or this operation, like, as a name. It's called Bonferroni. I can't spell his name, Bonferroni's correction. So the fact that you do this at a level smaller, like half the, so if you're doing 2 hypotheses simultaneously, you do it at alpha over 2. And then you're guaranteed that the test that you build by combining the 2 would have level alpha. What if I had tested 3 hypotheses simultaneously? Anyone knows what would happen then? Or how do we do the correction? So this in general holds. So the probability of union I from 1 to n ai is bounded by summation I from 1 to n pai. So this is sometimes called, oftentimes, union bound. This is the general form. Or Bool's inequality. Or one of the Bonferroni's inequality. So like the first Bonferroni, one of and Bonferroni. Okay, Bonferroni. He has multiple inequalities, but this is one of them. It usually it's called union bound. So how do we deal with the case where you have more than 2, like n? Suppose I'm testing not n, let's say m. What if you're testing m multiple hypotheses? This is called the multiple hypothesis problem. How can I make that correction? I'll do individual tests at a certain level, such that when I reject, when either one of them is correct, or when either one of them rejects, my type 1 error probability is at most alpha. So what should I take these individual ones in that case? Come on, guys.
It's just alpha over n, isn't it?
Yeah, so it would be alpha over m. Just test individual. At level alpha over n. So this, do it for yourself. This is just an extension of this. But I hope now you understand what this is about. So this is an example of doing a multiple hypothesis testing problem by constructing individual or tests for individual hypotheses, and then making the individual levels small enough such that when you combine them in this fashion, so you build a test that rejects, if either of these reject, if you do this correction, then that test would have a type 1 error probability, which is at most alpha. So you're guaranteed that. So is that clear to everyone? At least the case of 2 should be clear. Is it? Is there any questions? This was a detour, which was very interesting. I wasn't planning on this, but this is what happens when you do it spontaneously. Okay, so questions about this? So what is wrong with this? Why do we need to do anything else? So this seems to be working fine. Why do I have to develop more tools? So we didn't answer this. So we developed something, but it's not something really that sophisticated. It's just an adjustment to the original levels, and then you're done. So instead of doing it at like a specific threshold that we had, we're going to do it at a threshold which is slightly higher. So we're going to, or sorry, slightly higher. So we're going to be more strict about when the alternative occurs. So instead of like rejecting when the value is bigger than 2, we might be rejecting when the value is bigger than 3 to make sure that the type 1 error probability is small enough for individual ones. And you can see whenever, like, there is a problem with this. So if, like, say, anyone sees the potential problem here? Give you a few seconds to think about it. Anyone sees any problem with this approach? It's correct, but there is something. It takes too long? No, it doesn't take too long. Why would it take too long? Can you tell us why you think it will take too long? You're thinking of, you're doing it like individually for each one. Okay, so yeah, so maybe if that's the case, so maybe there is a single test. If you care about the time, there is a bit of an issue because there might be a single test which is time consuming to perform. Like you can construct a single, this is also a single test in effect, but it's just composed of multiple smaller tests. So it's not clear. So I'm going to talk about another procedure, which you probably know. And it might look like this is a single test, and it might be like look easier to compute, and it might be, but it's not. There's no guarantee that computationally it's necessarily easier than a t-test. So if you care about computational aspect, what I'm going to talk about may not be that obviously an improvement. But statistically, what's wrong with this? Why would, from a statistical perspective, we could probably do better? So think of what happens when m is very large. Suppose like m is 10. Like m is 100. I'm testing 100 simultaneous hypotheses. Yeah, so can you say that you were saying, or? So alpha needs to be small for each test, super small. So why is that bad necessarily? So when m is very large, alpha over m is going to be very small. So be it. So why that is a problem? It's on the right track. I just want you to think a little bit about it. Why would that be an issue? Okay, because in a way it's asking too much for the variables. Will fail to reject null very often. Okay, great. So that's the basic issue. So because alpha over m is going to be very small, you're gonna be very conservative in rejecting the null. So like asymptotically, when m goes to infinity, basically you're not going to do it, but you're not going to ever reject the null. To make sure that your type 1 error probability here is bounded by alpha. So in order to have like alpha 0.05, if you have 100 hypotheses, you have to test each individual one. So alpha equal 0.05 and like 100. So individual ones you have to test at level 0.0005, right? And this is very small, and your threshold would be very high. And most often you're not going to reject these. You're going to be guaranteed. So if you never reject the null, you're going to be guaranteed that this is 0. So you can always construct a test, which is very useless test, that always keep the null, never reject. And this will have perfect 0 type 1 error probability. But there's another piece that we care about in hypothesis testing. What is the issue with the test that always accept the null or not reject? Why that is a bad test? It's useless. Okay, but why? Can you elaborate a little bit? It is, but why is it useless? How can you formalize that statement? So the level is not the only thing that we care about. So there's a tension, trade-off in hypothesis testing. On the one side, there's type 1 error probability, or the level, which we want it to be small, but we can always make it small, make it 0 basically, by never rejecting the null. So there is another thing that we care about. What is it? It doesn't give us any information. Okay. Can we make it precise? How can I make that precise? What is the other objective? Okay, I'm not sure. Okay, everybody says she's not sure. Anyone has seen this before, or 100B probably? What are the two conflicting what are the two objectives in hypothesis test? What is it that you're trying to, achieve?
Are you referencing the type 2 error?
Okay, that's good. Yeah, so there are two things. So there are different ways to do it, but there is type 1 error and type 2 error. So what is type 1 error? What is type 2 error? This is the probability that I make an error under the null, or probability that I reject H naught, given that I'm working under the null. So what is this guy? Probability under what? Under H1. Okay, great. Don't reject the null. Don't reject the null under H1. Okay, which is 1 minus the probability that under H1 we reject the null, which is the right thing to do. Okay, sometimes you measure using these two, or equivalently you can do it using these two. So this is sometimes called, in engineering, this is called also false alarm. This is called detection probability. This is in radar, for example. This is like if you have if you're running a radar, or like some missile comes in, you want to make an alert people. If you keep sounding the alarm when there's nothing there, that's a false alarm. People are going to be not happy. But you also want to make sure, so you can never sound the alarm. That's the perfect situation, but you're going to some missile comes in and you never know. So you want to also detect the things. So whenever there is something there, so it's not like there's a missile there, you want to make sure that you detect it. So that's called the detection probability. That if there isn't actually something there, you want to reject the null. You want to sound the alarm. So this is also called in classification. This is there's another name for this. Anyone knows the name for this in classification? It's like radar terminology. So you're all off track now, you're just wandering around in your detour. So in machine learning, classification, this is called recall. So you can Google it if you have seen classification problems. This is out of all the cases that are positive, what is if a case is positive, what is the chance that you actually declare it positive? So you want this to be high. So you want this to be very large. You want this to be small. And so the test that never rejects has a perfect type 1 error, but the worst type 2 error. Type 2 error would be 1, or this detection probability would be 0. So that's why you don't want to do it. Another way of saying it in a statistic, this is sometimes called also the power language of statistics. So that's the power of the test. And you want the power to be large. Okay, so you want something that has a certain level, or basically maximum power. And this will lose power because you're gonna be very conservative in rejecting the null. So you most often do not reject the null. And so your test would have less power than the thing that I'm gonna discuss, okay? So if you somehow, because this bound is loose, so there's, this probability is gonna be there, you can see there's negative things and you have multiple, so you discarded this negative thing here. And if you have multiple ones, then you get like the other negative terms that you're suppressing. So this bound becomes very loose. And so you hope you can do better by jointly considering all the information. So if I might be able to come up with a test that directly tests this joint like null, and maybe I would hope that in that case my for the given level I would have a much higher power, and this is indeed the case. Okay, does that make sense to people? This is not the original plan, but this is good to remember. Okay, so in hypothesis testing, there are like this should be like something that you learn in a basic course on mathematical stat. So there's a trade-off in hypothesis testing between these two, and you need to pay attention to both. Okay. Questions? Comment? Clear to everyone? Oh, I see also bias and variance. So bias variance is another type of trade-off. I see Matt says this. It's related, but it's not in the context of hypothesis testing. This is more direct. So type 1, type 2 error, or type 1. And the detection or the power type, like a level, and so this is also called the level of the test, or significance level, versus the power. These are different names for the same thing. It's related in estimation with the bias variance, sort of. Here, type 1, type 2 error, or type significance level versus power. This is the trade-off. No questions, comments? All good? Okay, so let's go back to this. Hannah, do you want to continue? Okay. Yes.
Yeah, I think like after like where we left off in the video, I think we were talking about how we can rewrite this. So if we define like a linear subspace of the image of X, we find a linear subspace of that where like the matrix A times B equals 0, then we can actually rewrite our hypothesis test to be I think like mu equal, or like mu is in that linear subspace that we defined.
Okay, yeah, that's good. So let's how can let's try add a page here. Sorry, let me move this. So this goes say here. So there's like a footnote here. Why do we need to consider anything beyond t-test? Yes. So you looked at that. So as Anna pointed out, so I can write this in terms of so we know that y is x beta plus epsilon. We are working under this model. And so the mu here is x beta. It's the mean vector in regression. Under this general so under general MLR assumption, we know that mu belongs to the image of X. Is that clear to people? Why does mu belong to the image of X? Yes, okay. Why? Maybe someone wants to elaborate on this. Because it's projected onto the image of X. So this is, okay, it's a good point. So this is not mu hat. So mu hat is the projection of Y onto the image, right? That's true. So mu hat is the projection, and by definition, this belongs to the image. I'm talking about the mu, the original mu, which is what we don't observe. Well, that was a good point, though. It's good to make the distinction. Mu hat is definitely in the image because we're projecting it, but we're talking about the actual true mu, which we don't observe. Why this is an image? Isn't it because it's, yeah, okay, great. So because it's written as X times beta, and that's exactly the general form of any vector in the image. So if you go back to our discussion, that's how we represented the image. Image of X is the set of all vectors that can be written as X beta, where beta is in R to the, let's say, P plus 1. So as beta varies, this carves out all the image. So this is the general form or general formula for a vector in the image, and mu is in that form. So mu belongs to the image. So now what we can say is what do we know under the null? Or how about under the null? How about under the null? So under the null, I know that mu is equal to X beta. That's still true because the regression model still holds. But I also know, and I know that A beta is also 0. Okay, so this puts some restrictions on beta, so it's not any beta, but the betas that satisfy this. And so formally, I can define a new space. So this in your book is called L of X. And I'm going to change the notation or switch to that notation to be consistent with your book. I can define another space, the space of all vectors, such that they're like X beta, but beta satisfies A beta equals 0. So this restricts the set of betas that go into the construction here. And this I'm going to call LA of X, because your book calls it like that. And another way of saying it is like equivalent to saying that beta belongs to the kernel of A. So instead of looking at all betas, I'm going to look at all the betas that are in the kernel of A. That's like a formal way of writing it. If you remember what the kernel was, equivalently. This is like in parentheses. It's not necessary. But this defines a new set of vectors, okay? This is equivalent. And it turns out that LA of X is a linear subspace. It's another linear subspace of Rn. Do people remember what a linear subspace was? Anyone remembers?
Is it similar to the column space?
The column space is a linear subspace. Okay, Avery has the right answer. Yeah, so this image is a subspace. I'm claiming this is also the column space of X. This is another set, and I'm claiming that this is also a linear subspace. So linear subspace, as Avery said, is a set that's closed under vector addition and scalar multiplication. So add two vectors in this, it's there. And so you can think of this geometrically, these are lines and planes and things like this. So in the R2, linear subspaces is just the origin, that's the 0-dimensional one, and the 1-dimensional ones are the lines that pass through the origin. And so in R2, the linear subspaces are the set that has the 0 in it. This set, this is the 0-dimensional linear space. Things like this that pass through, these are 1-dimensional linear subspaces. And there's a single 2-dimensional linear subspace, which is the entire R2. In R3, again, this set is the 0-dimensional one, and then the lines are 1-dimensional ones, and then the planes are 2-dimensional subspaces, and then the 3-dimensional subspace, there's only one, which is just the entire space. So geometrically, there are these. Algebraically, there are things that are closed under vector addition and scalar multiplication. That was very precise. Thank you. So it turns out that this you can verify. Take any two vectors in this and then verify that the addition is in there. And if you take a scalar and multiply it by a vector in there, it's going to be still in there. So you just have to verify that it looks like this for some data that satisfies this. More, I can say more. So we also know that LA of X is a subset of L of X, which is this guy. So why this is true? Why can I say that this L of X is a subset of this guy? Anyone? Is it because it satisfies the same condition but with additional? Yeah, okay, great. So it satisfies the same, so it's the set of all vectors that look like this, but we have another, say, specification or a constraint on beta. So this is saying I'm looking at all the vectors that look like this for any beta. This is saying I'm looking at all the vectors that look like this for specific betas. And so certainly specific betas are included in the set of all betas. So the set of all vectors that look like this contain a set of vectors that look like this, but for a specific beta. So that's how you can argue it. So in both are linear subspaces, and both one is inside the other. So usually I represent it as one as a plane for simplicity. It may not be plane, it might be higher dimensional object, but I'll represent it like that, and then the other one I represent as a line here to make sure. In general, the dimension would be smaller. If you have constraints, that would reduce the dimension. It's not going to be generally on the same dimension as L of X, but that's the idea. Okay. So what we can say is that the null hypothesis is saying that mu belongs to LA of X, and the alternative is that it doesn't belong to this. That's how we can rewrite the hypothesis geometrically. The hypothesis that beta satisfies this is equivalent to saying that mu belongs to this constrained space. So the original regression problem assumes something about the mu. It just assumes that mu lies in this L of X. Okay, so the fact that you assume the regression already has some assumptions on mu. So you observe a vector y, and the minute you assume you're on the linear regression model, you're putting some restrictions on mu. Geometrically, you're assuming that mu belongs to this linear space. So you can see that's geometric interpretation of the constraints. Y might not belong to that space. We actually not, yeah, sorry, the y definitely does not because of the epsilon, but even the mean, so you're saying that the expectation of y, if I repeat the experiment many times and then average the vector y's, the average would be very close to this, or in the limit, it would lie in this. So that's the regression assumption. So mu would be somewhere here. Under the null, we're putting more restrictions, and we're in fact assuming that mu would be exactly on this. Within this, it's not going to be somewhere here. It's just going to be somewhere on this line. Okay, that's the further restriction that we have. So the general idea then is, so if you remember, regression, fitting a regression is like projecting onto this space. Okay, so when I fit a regression model, I basically project y onto L of x, and based on the residual will be the error of projection, and this would give me mu hat, and from this I can read beta hat. What we're going to do here is, if I'm under the null, I'm going to also project it onto this, because this is a linear subspace. I can project onto any linear subspace. Now I'm going to have a new mu hat A, and I'm going to have a new residual. And then what I can do is that I can compare this mu and mu hat A and mu. So I can compare this guy with this guy. Or equivalently, I can compare this residual with this residual. So I get two residual vectors, two fitted value vectors. And by comparing the two, I can determine whether I can design a test that tells me whether I'm under the null or not. In fact, the test that we're going to design is just compares or looks at this difference, mu hat A minus mu hat, or the square of it. And if this is large, you can conclude that you're not under the null. If it is small, then you can say you're under the null. So let me repeat. So we have two linear subspaces. Each linear subspace, you can think of it as doing a regression. The original one you already know. So for the original one, we project y onto this, and we get a fitted value and a residual. For this one, you can also think of it as another model with more restrictions. Now we're going to project, we can project onto it. I'm going to project onto it, I get this fitted value, and I get the residual vector. Now I have two fitted values and two residuals. Basically, I can compare, let's say, the fitted values. Equivalently, I can compare the residuals. And we're going to like reject H naught if this is large. So the question is how large it should be, but the general idea is reject it. This is a different test criteria or test statistic than what we had in the t-test. Does this make sense to people? Is it clear? Yes, okay. So we have 2 minutes. For the next time, I want you to think and look at the slides again, or the lectures, and think why it's reasonable to reject when this is large. I want you to argue for yourself that under the null, mu hat and mu hat A would be very close to each other. Okay, just the question. The fitted value is mu hat. So there are two fitted values. One under, so we're going to call this, in this context, we're going to call this the full model. And we're going to call the model in which you add this constraint. This is another regression model. This is called the restricted regression model, or we're going to call it restricted regression model. So there are two fitted values, two residuals, and each is associated with its regression problem. Okay. Okay. In fact, you can sometimes right. So, but I would like to think about y under H naught mu hat is close to mu hat A, and under H1 mu hat is far from mu hat A. So for this to work, we need this, and this is indeed the case. So in the lectures, there are examples. So I encourage you to think about it first, and then take a look at the lectures. So one way to see it is to assume the case where there is no noise. So think of the case where there is no noise. So y in that case would be equal to mu. And in that case, see what would happen if you assume that mu is some general vector here, versus the case where you assume that mu is some vector on this line. And in both cases, try to project, in that case, instead of projecting y, you're going to project mu onto both subspaces and see what mu hat and mu hat A has to be. Okay, so consider the noiseless case. So think about this and look at the rest of lecture 14 and some of lecture 15. And hopefully next time we can come back and discuss this further. This is a very important topic for us. So the more you spend time on it, the better. Questions, comments? Let's see if I have my video here. Okay, so if no questions, okay. So the next lecture is yeah, 14, 15. You still have 14 probably. Yeah, 14 and 15. Yeah. So take a look at the lectures 14 and 15 for the next time. We covered a little bit of it, more of 14. But this thing that we discussed here, I haven't discussed before, and it was very interesting, I think, that it came up, and it's worth going over this as well. And if you have questions, let me know. Okay.